Okay, so in this video I'm going to have a look at differentiation again, and I'm going to have a look at, in particular, rates of change. So I'm going to have a look at four examples. Now I've done the first one here for you. It's a fairly straightforward one. It's to do with a particle moving from a particular point, and it's given by this equation here. S is the distance from the point and t is the time. You can see it's a cubic equation here. But if you want to find the distance from a particular point at a particular time, t, you just put it in here. So if you want to find how far it is from the point after 2 seconds, put 2 in here, here and here, and it'll tell you in meters how far it is from the point. Now because it's moving at a certain speed. In order to work out its speed, what you need to do is differentiate s with respect to t. ds dt, I've done it out here. You get 3t squared, bring the 3 down, subtract 2, subtract 1 from the 3 and you get 2, and so on. So you get 3t squared minus 18t plus 15. This equation here, this expression here, will give us the speed of the particle at any particular time t. If you differentiate again, d2s dt squared, you get 6t minus 18. So 2 3s are 6, subtract 1 from 2, you get 1 here, and this will just give us minus 18. This here then will give us the acceleration. So you can take the distance formula, differentiate it, you get speed. Take the speed formula, differentiate it, you get acceleration. So now we have three formula, one for distance, one for speed, one for acceleration. So if we want to know, for example, here I've taken time t is equal to 6 seconds. What's the speed? Well, you just take your speed formula here, put in 6 here and here, and you get 15 meters per second, or 15 meters second to the power minus 1 is another way of writing it. If you want to know the acceleration after 4 seconds, so here I've taken a time of 4 seconds. I've taken time of 4 seconds here, so its acceleration then will be 6 times 4 minus 18. So that gives us 6 meters per second squared, or 6 meters second to the power of minus 2. So that's a fairly straightforward example. If you have an equation for distance, differentiate with respect to time, you can differentiate it with respect to time to give you speed, differentiate that, and you'll get a formula here for acceleration. Okay, let's have a look at example number 2, what I'm going to do. So example number 2. So this one here involves a wheel rotating through a certain angle. And the angle that the wheel is rotating is called theta. And it's given by the formula 3 times pi plus 20t minus 2t squared. So t is time. So you can find the angle that it's rotated through at any particular time. So if you want to know what angle has the wheel rotated through after 2 seconds, put in 2 here and here, and it'll give you the angle. And the angle will be in radians, by the way. We'll use radians here. Okay, so the first question is what is the rate of change of the angle with respect to time? The rate of change of theta with respect to time. What is the rate of change of theta with respect to time? So in other words, we're looking for d theta dt. What is the rate of change of the angle with respect to time? So you just simply differentiate this here. And when you differentiate it, remember pi is a constant. Pi is just a number. 3 is a number, so this term here is a number. So you just get 0 there. Differentiate the 20t, you get 20. Differentiate minus 2t squared, you get minus 4t. Okay, so if we want to know then, let's say for example the time at which the wheel comes to rest. So that's what we want to know. What time does it come to rest at? Well, it comes to rest when its speed is 0. Speed is 0. Or the rate of change of its angle with respect to time is 0. So in other words, 20 minus 4t will be 0. And you can see that if you solve that, bring the 20 over here, it becomes minus 20 divided by minus 4, you will get 5 seconds. 5 seconds. So it takes 5 seconds for this wheel to come to rest. Now another question that you might be asked here is, what angle did the wheel make in its final second? So in its final second. In its final second, what angle did it make? So what you can do here is find the angle it makes after 4 seconds. The angle it makes after 4 seconds will be theta, which is 3 pi plus 20t, 20 times 4, and then minus 2 times t squared, which is 4 squared. This was our original formula. That will give us an angle theta of 3 pi plus 48 radians. Now if we work out the angle it makes after 5 seconds, t is equal to 5 seconds then, we'll do exactly the same thing and we'll end up with 3 pi plus 50 radians. So this is the angle that the wheel makes after 5 seconds. This is the angle it makes after 4 seconds. So the angle then that it makes in its final second will just simply be 3 theta plus 50 minus, and make sure you put this part in brackets, 3 pi plus 48. And that will just simply give us 3 pi plus 50 minus 3 pi minus 48, and that just simply gives us 2 radians. So in the final second, the wheel rotates through an angle of 2 radians. Okay, so that's our second example. Let's have a look at another one. Let's move this up here, and this is number, I think, 3. So, okay, in this particular example, we're going to look at a snowball, and the snowball is melting, and it's a spherical snowball. So let's assume it's spherical anyway. So we'll take our spherical snowball. It has a radius of r, and it is melting at a rate of 20 cubic centimeters per hour. So 20 cubic centimeters per hour it's melting. Okay, so its volume is decreasing by that amount every hour. Okay, so the first question is then, what is the rate of change of the radius? What is the rate of change of the radius? The rate of change of the radius is dr dt. What is the rate of change of the radius? Now, let's just have a look at, we're going to end up using the chain rule here really to work this out. So what we're going to do is look at what we've got so far. This is what we've got so far here, this minus 20. What is that? That is the volume changing with respect to time. This is the volume, this is the time. So this is really dV dt, the volume changing with respect to time. This is dr dt. So if we wrote down an equation here with dV dt in it, dV dt is going to be equal to dr dt times, well actually, I might write this a slightly different way here. dV dr, let's take the dV first. dV dr times dr dt. This is our chain rule really. So dV dt, which we have here, is equal to dr dt, which we're looking for, times what? Well, we need to, we want dt on the bottom here, which we have. We don't need the dr, so we need to put a dr on the bottom of this part here, and we need dv on the top here. So if you look, the dr's here, if you like, will cancel or divide into each other, and we're just left with dv dt here. So what have we got? We have this. We know that this is minus 20. We're looking for dr dt. What we don't have at the moment is dV dr. So how are we going to work this out? We need this. We have 3 things in this equation. We need to find this one. So we need the other 2. And we only have one of them. So we need this one here. How are we going to find that? Well, it's the volume and the radius we need to look at. The volume and the radius. Well, if you look at the volume of a sphere, what's the volume of a sphere? Well, let's write it down. The volume of a sphere is 4 over 3 pi r cubed. Well, now we can differentiate volume, dV, with respect to r. That's exactly what we want here. Look, dV dr. dV dr is going to be equal to, remember, r is our variable here, so bring this 3 down, it'll cancel with this 3, and we're just left with 4 pi r squared. 4 pi r squared. That's perfect, that's exactly what we need. Now we have our dV dr. We have it in terms of r, that's fine. So we have this, we need to find this. So let's just write everything we have down underneath here. So let's see. dV dt, that's going to be our minus 20. dV dr we've just worked out as being 4 pi r squared. And our dr dt, we don't know that. That's exactly what we want to find out. So I'm just going to move over here now. Let's divide across. So our dr dt is going to be equal to minus 20 divided by 4 pi r squared. 4 pi r squared. So that will just give us minus 5 over pi r squared. So this is our dr dt. This is how the radius changes with respect to time. That's exactly what we're looking for. So for example then, if we were asked to find the rate of change of the radius when the radius is, for example, 2 centimeters, all we've got to do is put 2 in here. So in other words, dr dt is equal to minus 5 over pi times 2 centimeters, 2 in this particular case. So that would just be 2 squared, which is 4. So it's just going to be minus 5 over 4 pi in this particular case. Okay. Now let's have a look at another one. Let's have a look at maybe the surface area. What is the rate of change of the surface area? The rate of change of the surface area. So let's have a look at that then. Now we know that we know dr dt, by the way. I'm just going to hold on to that particular one, dr dt. I'll just put a line underneath this. So dr dt, we know dr dt is equal to minus 5 over pi r squared. We may need to use that in this section. Let's have a look anyway. Now we want to look at the rate of change of the surface area. The rate of change of the surface area. So that's going to be let's say SA, we'll call it SA, dSA with respect to time. The rate of change of the surface area with respect to time. So what's that going to be? That's going to be dSA with respect to, again, or, we're talking about or, and I'll put the dr up here as well because I need to get rid of it because there's no r on this side, and down here I need dt. Now let's see what we want here. We have we want to find this here. We want to find dSA with respect to time. We have dr dt. We know that that's minus 5 over pi r squared. This we don't have here, dSA with respect to r. That's something I need to work out. Okay, so let's do that. So I'll do that over here. Okay, so let's see, dSA with respect to r. So I need surface area and radius. Surface area and radius. So the surface area of a sphere is going to be 4 pi r squared. It's 4 circles, if you like, 4 pi r squared, surface area. Now dSA then, with respect to r, which is what we want here. I have SA here, I have r on this side. That's perfect. Bring the 2 down, that gives me 8 pi r. 8 pi r. So now I have dSA with respect to dr. Okay, so now I have this, that will give me what I'm looking for. the rate of change of the surface area with respect to time. So let's do that then. So that's going to be dSA dr, so that's going to be 8 pi r, and then we got to multiply that by our minus 5 over pi r squared. So that will give us then just simply, let's see, 8. Let's see, our pi will cancel anyway. One of these r's will cancel with one of these, and I'm left with minus 5 times 8. So that just gives me minus 5/8 minus 40. Minus 5/8, that will give me minus 40 over the pi's will cancel. I'm left with r down on the bottom here, and that's it really. So that's the rate of change of the surface area with respect to the radius. The rate of change of the surface area with respect to with respect to time, rather, I should say, in terms of the radius here. So that would be centimeters squared per hour. Centimeters squared per hour. Okay, so that's it. And I mean, so if you want to know what the rate of change of the surface area when the radius is 5 centimeters, for example, you would just put 5 in here and you would get minus 8. So the rate of change of the surface area with respect to time when the radius is 5 centimeters would be just minus 8 centimeters squared per hour. Okay, so that's another one done. Let's have a look at one more. So let's see, let's move up again. Right, this is number 4. So now in this particular case we're going to look at a metallic cube. So let's have a look. We're going to have a look at some kind of cube here, and the sides, or the lengths of the sides of this cube we call x. So it's going to be x, x, and x here, length, width, and height. Now, this particular cube, metallic cube, is being heated. So the side lengths of this cube is expanding, and it's expanding at a rate of 0.2 centimeters per second. So 0.2 centimeters per second. These are the side lengths are expanding. So what does that mean? The side lengths are expanding at a rate of 0.2 centimeters per second. That is really dx dt. That's the rate at which x, or the lengths, are expanding, dx dt. So we know that. Now, what we want to do here is find the rate at which the cube's surface area is changing, the rate at which the cube's surface area. So we're going to look at the surface area of this cube. So what we want here is we want dSA, the rate at which the surface area is changing. So this is going to be dSA with respect to t. So this is what we're looking for here, dSA with respect to t. Okay, so dSA with respect to t, what is that then? dSA with respect to t. So if I write that down again in terms of the chain rule, so that's dSA dt, that's going to be dSA with respect to, now we're talking about x here in this case, so it's going to be x here, and then the x dt. So again, the x's will cancel here, and I'm just left with dSA with respect to dSA dt on the left hand side as well. So we want to find this here. We know dx dt is 0.2. What about dSA with respect to x? We don't know this bit here, so this is what we got to work out. So we want to work out some kind of an equation with surface area and x. Well, what is the surface area? Let's have a look at that. The surface area of a cube, well, the area of one of the squares here is just going to be x times x, or x squared. There are 6 surfaces, all exactly the same, so it's just going to be 6 times x squared. So then if we differentiate the surface area with respect to x, dSA with respect to x here, we get 12x. So now we know this. We know this already. We were given that in the question. So now we can work this one here out. So let's do that. Okay, so our dSA, rate of change of surface area with respect to time, is dSA dx, which we've just worked out as 12x. I'm going to multiply that by the x dt. The x dt is 0.2 centimeters per second. So that will just give me 0.2 times 0.2 times. So that's 2.4x. So that's just simply going to be 2.4x centimeters squared per second. That's the rate of change. That's how fast the surface area is changing with respect to time. So if, for example, we want to work out how fast it's changing after 5 seconds, no, sorry, I'm not talking about time anymore. Let's say when x is 5 centimeters. When x is 5 centimeters, that's what x is. We're not talking time anymore. We're talking about distance x here. So if we put 5 in here, for example, that will just give us dSA with respect to time is equal to 2.4 times 5. So that will just give you 12. So that will give you 12 centimeters squared per second. So that's how fast the surface area is changing with respect to time at 5 seconds, after 5 seconds. Okay, so let's look at volume now. Okay, so we're going to look at the rate at which the cube's volume is changing. The rate at which the cube's volume is changing. So it's the same kind of thing again. Okay, so we're going to write down an equation, chain rule equation, with the volume. So what we're looking for is dV dt. So again, we write down dV dx, and then dx on the top, just to cancel it, dt. So this is what we're looking for now. Now we're looking for this. We know what dx dt is. We've worked that out up here. Dx dt is 0.2. We didn't work it out. We were given it. So we know what that is. We know we can stick in 0.2 here. What I don't know is this. And we're looking for dV dt. So I got to work this bit here out. Now dV dx is what we're looking for here now. So let's have a go at that again. So let's do that over here. So we want an equation with volume and x in it. So volume of a cube is going to be x times x times x. So that's x cubed. So dV dx then is just going to be simply 3x squared. 3x squared. So now I have dV dx. So I can just stick 3x squared in there. And that will give me a total of 0.6x squared. So that's how volume is changing with respect to time. And again, if x is 5 centimeters, let's take x as 5 centimeters. How is the volume changing with respect to time? So that's just dV dt is equal to 0.65 squared in this case. So that will give you, let's see, for 5 is 25, 0.6, that will give you 15, this time cubic centimeter. We're talking about volume is changing with respect to time, volume in seconds here, cubic centimeters in seconds. So it's 15 cubic centimeters per second is how fast the volume is changing. Okay, so that's it on rates of change.